Welcome to your first subject audit enhancement webinar. So this is the first one of the second year, and I'm going to start by telling you about the course, and then we've got a little bit of pedagogy, because that's part of the course, and then we've got the maths. So today, as I just said, module content, theory, and then some maths, which is proof and qubits. So first of all, just in terms of the timing going forward, last year we had 3-hour webinars, but 5 of them, supposedly. I think you might have had, you managed somehow to get an extra one. I'm not quite sure how it's worked. But now what they've done is they've now done 6 2.5-hour webinars, which is going to be interesting. So we're just actually going to have this, well, the same material, because I've written 6, but I've written 6 3-hour ones, so we'll just be trying to squeeze it in and see how it goes. So I've put them as 9:15 to 12. That's a little flexible if you guys do want to change that, because my daughter's school drop-off is 8:30 as it is, so I can do it a bit earlier, I can do it a little bit later. So that was kind of in the middle. So 2.5 hours, really, I've put in a 15-minute break in there, but I think we could also have a 15-minute break included, so we could end a bit earlier if you want to. So, busy slide, but it's basically just the aims that come out of your handbook for the second module. So you're going to be level 5. They've got all the descriptors that are just the same within the handbook. And the key bits really are that you are going to be able to articulate a command of subject knowledge, analyse classroom practice, and understand the relationship between subject knowledge and pedagogical decisions. It's just a case of, pushing you on from where we were last year. So the difference really is that last year was more about you getting to grips with just subject knowledge. The idea is that this year there is more theory in it, and a slightly higher level of math. So I think there's a development of a deep and profound understanding of mathematics, engagement in mathematical activity, analysis, exploration of different perspectives on the nature of maths, exploration of big ideas, and then evaluation and discussion, trial and evaluation of pedagogical strategies. That's quite a bit of it, as you're always doing, and as well as the same sort of the personal subject of pedagogical knowledge. So it's just, here's the spreadsheet. This is quite small, isn't it? But here we are, having our first webinar. In each webinar, and in each session, in fact, whatever we're doing, that I do with you, there will be a little bit at the beginning about some aspect of maths theory, maths-specific pedagogy, I would say. So looking at influences on maths pedagogy, the curriculum, theories of learning, various different teaching approaches and stuff like that. Actually, some of it is a sort of general thing that then I've sort of taken and looked at specifically what does that mean for maths. It's lots of the things that we've already been talking about, just formalised basically in a couple of slides before we get into the maths. So I've put this spreadsheet on Student Central, so you can see what's going on for the whole year. In terms of some changes going forward, based on the feedback that was received from Cohort 1, was mainly that there was too much for them to do towards the end. So I think you've got less self-studies, and in fact your assignment is due fairly early. It's due in February. So you kind of get that out of the way fairly early on. So the learning outcomes are exactly what you need to meet in the assignment. So you need to be able to demonstrate a depth and systematic understanding of key ideas in math, analyse and critically reflect on the impact of your subject knowledge on your pedagogy, and critically engage with and analyse the relationship between theory, policy and practice. So it's all about making sure that, you know, when you write your assignment, that you are hitting each of these targets, each of these outcomes. So just to tell you about the assignment, so that you know what you're going to be doing. In February, at the intensive study week, which is the week after half term, you will each do a 15-minute presentation, then questions, to your peers. So they'll muddle up all of your secondary cohort. So you might be presenting to some of the guys doing PE or physics or whatever into small groups and present to them. And then you submit, I think it's either that week or the next week, the sort of the written presentation of what you've said. And so within that, you have the opportunity that although there may not be everything that you wanted to say, you can put it in the written bit that you submit. And effectively, I will have made notes on the day of what you've said, and then I will have read through your written bit and marked that as well. Sorry, I realised I should have bought a glass of water. So in terms of going forwards, you can get going on this assignment right away, because you know the sooner that you've done it, the sooner you've done it. So I haven't got a final steer exactly on whether this will be changing, but I've taken this from what was given last year. And they were told that you to select one topic from within your subject area. So that doesn't necessarily have to be, for example, algebra, but it could be. But it could be more something to do with an issue and how it is in math, such as gender, better for learning. And we've talked about this, haven't we? You know, getting girls, you know, how do you make more interesting for girls? Or you can talk about some specific things that you might have done. So a resource that you made. So someone last year had this really great sort of learning map they've made. So the students come in, they've got a learning map there. It was basically for literacy. And then when the students are stuck, they can look at things. It was for science literacy. And what he did was he talked about the research behind it, so the theory that was behind literacy in science and that sort of thing. And then he'd created this thing, and then he talked about how it, you know, how it had gone in relation to the theory and that sort of thing. So you can do that sort of thing. And it is up to 3. We did find that the people who'd done 3 found it difficult to give enough time to all 3, because that's only 5 minutes and it goes so quickly. So, you know, one topic, 1 or 2 activities would be my advice. So these were the guidelines that was given in terms of just the step-by-step, you know, so talking through what you chose, getting a theory and deciding what you did, you know, talking about what you did, and then exploring the impact on pupil progress. It's one of the important things. What impact did you have on pupil progress? I mean, you can say it was rubbish, you know, but as long as you evaluate it, then that's then that's fine. So that's the information about the assignment. I briefly talked to you about it at the last ISW. Any questions about that before I move on? Okay. Well, it's there in the PowerPoint. I've put this PowerPoint up on Student Central as well, so you can look back at that. I've also, I think I've put a key document or assignment, put this, Carol basically wrote up a guideline document, so that's in there. So, feel free to get started on it as soon as possible, and you can email anything to me that you want to ask about, and that sort of thing. The ones that did well had basically written their presentation as a sort of like an essay. So they were like, so Dweck talks about this, and based on that, I did this, and all, so that you are speaking more more freely than that. But it's almost like it's an essay with all the theory and stuff that you normally put, but you are talking about it. And you must bring in the theory. There were two specific things. So you must bring in theory, rather than just saying what you did and how it went. Otherwise you won't sort of get enough on that strand otherwise. And you must relate it to maths, rather than just talking about assessment for learning generically. You need to really be specific about it to maths. Right. So the pedagogy for today, the theory for today, is just thinking about the purpose of maths education. I'm sure this is the place to start, isn't it? So when you're at school, it involves a bit of interaction. Either you can talk or type. Yeah, when you're at school, were you really bothered? Did you just do it because they told you? Why did you think you were learning maths? Anyone want to offer an opinion? Because you had to, says Adam. Will?
Yes.
Why did you think you...
When I was at school, when I was at school learning maths, I was, because I had a fairly clear ambition as a teenager to go and do engineering at university. I always knew that was the route. I had to know about mathematics to be able to follow that path. Admittedly, I didn't after about age 19, but I always had a purpose to it. So I was kind of odd in that respect.
But of course, the vocational aspect is, I suppose, the main driver that we often use for this, isn't it? It's sort of, you need this.
I mean, it's only recently you sort of appreciate that it's sort of problem solving and it's how everything is. It's analysis of everything in terms of the natural world is very much mathematically based. But yeah, it was because I wanted to be an engineer. To be an engineer, you need to be good at maths.
And going forward, why do you think we teach maths?
We teach maths, I think, because it's whilst the specifics are not always completely relevant to everything as a person in life, the ability to analyse something inherently abstract, which is a problem, and work out a solution using a set of rules is a very, very important skill.
Yeah. What I want you each to do is to just, if you've got a piece of paper handy and a pen, write a statement outlining your personal vision for maths education. Because people, I guess probably as maths teachers, we may not differ so much from each other, but a lot of people have very different ideas of why we have maths education. And I'm going to get you to just do that now so that I can go and get a glass of water. Okay, so have a go at doing that, and I will be back in a minute. Right, does anyone want to offer their personal vision? Jerry, what have you written? So Jerry's written in the question pane. I don't know if everyone can see that. But he says, maths touches everything we do in life, both in and out of it. As a subject, it allows us to develop reasoning skills which are useful in a variety of other subjects and real-life situations. Yeah, very all-encompassing, isn't it? Maths. Imagine if we didn't teach it, especially as a core subject, which I imagine at some point it must have been not a core subject. And yes, I imagine that fairly shortly they realised that we did a bit of arithmetic and then gradually developed from there. Anyone else want to share theirs? We've all gone very quiet. Wow. Okay, so Will has written, in 1961, JFK said, we choose to go to the moon. That created a problem that could only be solved by utilising mathematics. It is a language in which the universe communicates, and to understand this, we need to understand maths. Math education serves to open the door to this world and teaches the ability to look at problems and applying a set of laws to work out a solution. Well, Adam, you've got quite a lot to live up to now. I will just click onto the next slide. Oh, I did have one. Oh, I think I put it on PowerPoint, sorry. Sadly, you still sound like a Dalek. Oh dear. Well, anyway, I will we'll come back to you if you want to go for it. So, I don't know what his first name is, but his surname is Ernest. Wrote about there being 5 different views, because the views that you've put are very much about how mathematics is, the only way that we sort of can understand the world in which we live in, and therefore, it's particularly useful. And he sort of split people off into their different views, because there are a lot of people that you come across who are really like, well, you just need to be able to do the numeracy. So they are referred to as the industrial trainers. You just need to acquire the basic skill of numeracy. And also the social training in obedience is just the fact that do this, you do it, you get an answer. Just being able to do that. So what's Adam said? Maths, as you said, maths encompasses everything being able to problem solve and reason, not only mathematically but logically. And so it's all about the skills that are transferred. And that is sort of the technological pragmatists are concerned with people being able to learn basic skills to solve practical problems with maths and IT. I think when I was at school, I would have been more of an old humanist, a purist, which was that the aims are to understand and work with advanced maths and gain an appreciation for maths, because I just loved it for the sake of it. And I actually really wasn't interested in the applications, and only now, as I grew up, appreciated that my ability to work with symbols and that sort of thing really helped me with my languages and music, and thus the sort of transferable skills that were there. Progressive humanists have quite high aims that children gain confidence, creativity and self-expression through math. I'm not really sure how many teachers or children in particular would put that as their initial aim for math learning, for learning math. But it's a nice one to have. The public educators, so I mean this is really where we're coming from, aim to empower learners to be critical and mathematically literate citizens in society. And I think the point is that at whatever level that is for you, isn't it? So if you require the numeracy and just need to have the basic skills, then that's fine. But we need people at all levels. Well, we need everyone at that level, and then we need the people who are going to be accountants and business and that sort of thing. And then we need engineers, and then NASA science, space scientists. We need the really high-end complicated stuff, and all the IT and programming and computing side. It's sort of coming into its own as well. So really, it's the fact that with maths we start from a very abstract point, which is tricky, isn't it? Because not many people appreciate that just because it's fun, just because it's abstract, or can comprehend it in its abstract form. Actually, I suppose we go in and out, don't we? Because we start with very small children. You're given a number of blocks, and then that becomes numbers, and you do things with those numbers. And so it starts off, quite real, becomes abstract, and whereupon you end up just process crunching. You just, do this, find this, do this, find this, do this, find this. You get lost in what it actually means, and then you come back out again much later when you can really appreciate, okay, so in real life, this is how it works. However, not many people get back to that point. And there is much more of a push nowadays, isn't there, that we don't just say, okay, today you're going to learn how to do this, do it. We bring in, as the teachers, our role is to bring in why we're doing this, where this is used. Sometimes it does, often at their level, they have no more requirements. For example, today I'm going to be showing you how to solve cubic equations, like quadratic equations, those sorts of things. It may not seem that there is any real life application they are ever going to use that. However, were they to design surfboards, which could be modelled by a really slim parabola, it could be really useful to use quadratic equations to do that. And if they wanted to use a 3D printer going forward, they'd need to be able to input those equations in order to get it printed correctly, which may to them seem absolutely absurd, but before we know it, we will be there. So thinking about what each of these views mean in terms of teaching, I've come across a lot of teachers who are industrial pragmatists, who really just think, right, you need to develop these skills. Very much, if you go into any sort of functional skills classes at the lower end, you often find, right, we just need to get them through this, get them to fill in this spreadsheet of what they spent today, do a total, or work out an average or something. So they take a real work situation, get them to figure it out, and they just do that repeatedly until they basically get it. Well, they don't really get it, actually, but until they can just do what they're told. I think it's quite easy to sometimes fall back into this. When you get the kids, you don't have enough time, you've got kids that really struggle, and you think, okay, I'm just going to have to plug it out and just keep on at it. They'll eventually get it. And I know that with a lot of bottom sets, teachers fall into this in the hope that something sticks. And I think there's a lot of theory to say either way, whether that works or not. Ultimately, I think it's boring for everyone, so why not try something else in the hope that it works, that something else works, and make it all completely fun and, but practical and real life and appeals to the kids rather than repeated practice. Although, of course, it's difficult because they need the repeated practice as well in order to develop skills. Oh, the conflicts we have. The purists, these are my headmaster who used to teach us at primary school. Hilarious. He used to walk in. He wouldn't have decided what he was going to do until he got there. And he'd be like, right, today we're doing binary. And we were 7, and we were like, okay, whatever. He just wanted us to know maths. He really, would just stand at the front, tell us a lot of stuff. And, it was all about rigor and precision. I think the progressive, teacher acts as a guide for each individual's voyage of discovery. I think that obviously comes into what we're doing. This would be amazing if you had quite a lot of time. And as a tutor, I think this is where, obviously I do quite a bit of that. But really, public educators, teacher encourages students to discuss problems, make them more relevant to their lives, as we were saying. And then, group work and all sorts, and you sort of bring them together to work together and develop other skills, the problem solving and the logic as well. So that is the theory for today. And there's a few more books about that have a bit of things about that. Anything anyone wants to add? Right, let's get on and do some maths then. Proof. We did talk about proof briefly when looking at some of those horrible questions last term. So within the new GCSE curriculum, I keep calling it the new one. I will continue to call it that for quite a while. They are expected to be able to do geometric proofs. So the applying angle facts, triangle congruence, similarity, all of those sort of things, which we've talked about before, so that when you are solving some sort of geometrical problem, you have to state an angle fact, and that provides the proof. So angles on a straight line add up to 180, therefore I know this angle is such and such. And equal angles and equal sides, oh, it must be an equilateral triangle. You know, those results that you know, which lead you to make conclusions. So there's that side, but we're not really going to talk much about that today. Then there's the other side. So know the difference between an equation and an identity. Argue mathematically to show algebraic expressions are equivalent, and use algebra to support and instruct arguments and proofs. So, here is this, the geometrical ones that they're expected to know, and we've talked about this before. Yeah, typical GCSE questions. You've got to find this angle using all sorts of different results. But algebraic proof. Whoops, sorry, I meant to have each of these arriving rather than one. Deduction. So this is basically logic as we see it. You go through a mathematical argument using mathematical language. So this is where the students start to struggle, because already we are taking something that could be a real life situation or could be something abstract. We are defining it in terms of symbols. So they have to interpret it and put it into the appropriate language. So, for example, some of the things that they'll need to know is that when we are talking about an even number, we can use 2n, because any number n multiplied by 2 is going to make it an even number. And an even number is anything that divides by 2. And likewise, an odd number can be represented as 2n plus 1, also 2n minus 1. It doesn't matter which one they choose, whatever they're doing, it will still work out. So part of learning to argue mathematically involves learning the language initially. So being able to symbolize and read the symbols. So this is P implies Q. So that means if P is true, then Q is true. So a lot of people talk about necessary and sufficient. This way we say P is sufficient for Q. If it was the other way around, the arrow, then that would mean that P, oh whoopsie, so don't need to have a B there. P is necessary for Q rather than B. And both ways, it means P is true if and only if Q is true. So P is necessary and sufficient. I've never really got on well with the necessary and sufficient because it's a lot of words and the kids get muddled between them. So I tended not to use them. You don't need to. I know traditionally it was the terminology that was used. They don't use it in the exams, particularly. They don't, they're going to be given in AS level, in particular, they'll give them symbols. And GCSE, obviously, they're not expecting them to use this. They're just saying, okay, if you can explain what it means, that is fine. you don't have to use the terminology sufficient and necessary. So I tend to just let them say, okay, if this is true, then this is true. And to just generally interpret that in respect to whatever it is they're given. So, for example, they're told that the theorem P, or the lemma P, is y cubed is greater than 1. And that Q is the statement y is greater than 1. So looking at these two statements, P and Q, what can you say? Thinking back to this whole, arrows, P implies Q, or Q implies P, or both. I'm going to scribble some numbers down. So what do you think? Does P imply Q? Does Q imply Q?
Q.
Yeah, go on with that one.
P, because if y cubed is greater than 1, y has to be greater than 1 because 1 cubed is equal to 1. Just trying to think if P implies Q. Yes, it does, because if y cubed is equal to 1 or less than 1, y's got to be less than 1 as well.
Mm-hmm.
I think.
Yeah, I think so too. And in terms of, how we think about these things and figure it out, we try a few numbers initially, don't we? And see, okay, it's true for that, it's true for that. Can I find one that doesn't work? And then we sort of, conclude, okay, well, in that case, I think in this case, P and Q imply each other. But we haven't actually proved that. So at the moment, we're just talking about sort of the symbols. And in the AS papers, the students are often given this sort of thing, and they're just asked to write either P implies Q or Q implies P or both. At GCSE, obviously, we haven't really seen much about what they're asking. But that question that I showed you last time, where it gave the definition of something to do with times, wasn't it? I don't know what it was. But they could set this all up and ask them to do it. But I'm not sure that that's likely. Now, going forward, the next thing is it did say that they must understand the difference between an equation and an identity. So do you know the difference between an equation and an identity? Adam, do you still sound like a Dalek now you've logged off from the phone again? Oh, yes, you do. Right. Jerry, what do you mean by equal sign? So obviously that's the visual difference.
If you're not, an equation is equating one thing to another. So it will normally say this equals that.
Yeah.
Y equals 3x plus 5 or something. Whereas an identity just, has the symbols but doesn't equate it to anything else?
Yes, I think it is difficult to describe. An equation. I think the example you gave, actually, y equals something, is more likely to be a formula, because an equation we are looking to solve in order to find out what the value.
Yeah. Okay. So yeah. Okay. Right.
Whereas, yes, I mean the definition of an identity.
So x plus 3 equals 5 then. So
yes.
that would be your equation.
Yeah. Yeah. Exactly. Although I suppose, yes, you're right. It could just be that there are two unknowns and it's really possible to solve. Oh, no, because it's not impossible to solve, actually, because, of course, the thing about a formula versus the solving the equation is that that is true for many different values of x and y, isn't it? More like, in fact, an identity. So the identity the equation you solve is just true for that one value. You find that solution. Whereas for an identity, it is always true, provided you put the same numbers in both sides, you get the same result. So they are identically equivalent, is what I want to say. But of course, the identical is in the word identity, isn't it? So when the students are expected to prove an identity, what they're looking for is for them to take each of those sides and make them look identical. So I want you to have a go at doing that now, actually. So this identity, prove this identity. Now, in terms of the triple line, the triple equal sign, or the equal sign with a line above it, it's not the end of the world if the students leave that out. Often as they're going down it, they forget, and you find that it becomes an equal sign. And that's fine, because ultimately it is still equal. It would be more of an issue if they were to add an extra equals line on an equation. So, yeah, work through both sides, trying to make them look the same. And effectively, when you're teaching this to the kids, what they've got to remember is they've got to do it algebraically. You'll find that they look at that and they go, okay, I can prove this identity. I'll put x is 1 and x is 2, y is 2 in both sides and show that it's equal. I've just marked an exam where there was something like this. We gave them a mark for doing that, but really we want to see it done algebraically. And it's nice to set it out often by them saying left-hand side, and they just, in this case, multiply it out, and right-hand side, and then saying, therefore, left-hand side equals right-hand side. So, here we go. So, what did you get on both sides? Sorry, Jerry, I'm just going to mute you. Or can you mute yourself? Oh, yeah, 9x plus 1. Excellent. So that is exactly it. So because they'll have got 9x plus 1 both sides, then they have proved it algebraically. So we've got two more things here that you can prove. Your written language needs to be put into symbols, you then muddle the symbols around and draw a conclusion from it. So I want you to have a go at, without any hints, coming up with the proof for this. The sum of any 3 consecutive even numbers is always a multiple of 6. And put your hand up or type it when you've done it. That's true. Every third even number is a multiple of 6. Oh, yep. So, yeah, algebraically, exactly what Will has written. He's put 2n, so that's the first even number. The next even number is 2 more than that, so 2n plus 2, and the one after that's 2n plus 4. You add all of that together, you get 6n plus 6. So you can take the common factor 6 out, showing that if you add any 3 together, whatever you have will be divisible by 6, be a multiple of 6. It's a really, in fact, I'm going to write it on here for Alex for when he watches this. So 2n is the first even number. You add on the second number, which is 2n plus 2. The third even number is 2n plus 4. We add that collecting the terms, we get 6n plus 6, which is multiple of 6. And I mean, these sort of proofs, obviously presenting it like this, the kids have no idea where to start. They've never seen this sort of thing before. So you could start from completely the opposite end and give them a load of numbers. So you give them loads of cards that have got like 2, 4, 6, 18, 20, 22 or whatever. Get them to add those up, see what they notice and that sort of thing, and then see if they can generalize that and get towards this, more of a sort of discovery. So then once they've seen this, and they should put a conclusion, therefore, it's always multiple of 6. But then they'll think, oh great, now I know a little trick. I know how to write even numbers in the next ones, and that if I try and take a factor out, that's how I show it's a multiple of 6. So that can help me. And then then they know what they're looking for each time. So here, if you multiply 2 odd numbers, you get an odd number. So they're thinking, okay, so I know I'm going to need to end up with something involving 2n plus 1 or 2n minus 1 again. So have a go at doing this one. If you multiply 2 odd numbers, you get an odd number using this type of reasoning. So you might want to get the students, first of all, to clearly identify what they think they're going to be doing. So multiply two odd numbers. So the first thing is you need two odd numbers. Now, they don't actually have to be different. They can be the same odd number, or they can be a different one. It won't matter. I think I will use the same odd number, because it doesn't matter, because all they have to do is they're only representing an odd number. So when you multiply that out, you get 4n squared plus 4n plus 1. So already I'm delighted because I know that I've got this plus 1 in. Yeah, so Will's done the same thing. He's just chosen two odd numbers, 2n minus 1 and 2n minus 3. And he's ended up with the 4n squared minus 8n plus 3. Yeah. So exactly what you've then done though is you've taken out the 4n. What you really want to do is take out the 2, because effectively what I want to do is get something that looks like 2n plus 1 or 2n minus 1, some sort of odd number. However, they're absolutely fine to justify it if they've done it. So if I take a 2 out, in here I'm left with 2n squared plus 2n plus 1. Now, whatever's in here, it doesn't matter, because we're going to multiply by 2 and add 1, which means we're going to make an even number and then add 1 and make an odd number. So often what we do is say, okay, let that be k. So therefore this is 2k plus 1, and therefore is again the same representation of an odd number. The students struggle with this. You find them going from this to then saying, therefore they've got 2n plus 1. And of course they use their n in two different ways. I've done it back to front here. I think I have a tendency to actually start with things being k for the basic ones, and then ultimately making it an n at the end. But it doesn't matter, and you don't want the kids to get hung up on a particular letter being a particular thing, because that's just not the case. So they can just say, let this be, whatever they want to call it, p, if you want, and therefore that's 2p plus 1, and then they put the conclusion, which is an odd number. And because they've done it in a way in which it's algebraic and it's worked through logically, that is then true for all odd numbers. So Will, with yours, where you did 2n minus 1 and 2n minus 3, and you've got 4n squared provided we take a 2 out of the front bit, and we can do +3 because that's still an odd number as well. You could also split that off if you really wanted to, so that you could bring in, I could actually split that off so that I've got +1 inside the bracket and then another +1. Does that make sense, what I've done? I'm trying to cross that out and make it worse. Right.
That makes sense. I mean, essentially, you've got a number that has, either way you do it, you've got a number that has to be even, to which you're adding an odd integer to, which is going to be an odd number. So therefore, it proves it.
Yeah. And I mean, this bit here is just making it just for nicety, really. This ability to split numbers up into 2 bits, so that I'm just splitting that into a 2 and a 3, and sorry, a 2 and a 1, because +3 is the same as +2 +1. And I've just decided, oh, I want the +1 on the end, so I'm going to take the +2 in with this bit. So when I take a factor out, I can take it out of all of that, and then that is my new K or whatever, and I've still got my so just these little tricks of manipulation come with age and experience, really. Some of the kids get it right away, but I would say less than half, definitely. And a lot of them find this, I'd say the ones that are going to go on to be mathematicians, this is what they love, but everyone else is out there going, when am I ever going to use this? Who cares at all? So I think that's where sort of the fun and the magic and the, you know, like being able to do tricks and that sort of thing with it is where this sort of stuff works out, about why that's true. So there is certainly no algebraic proof like that, being able to deduce things. They're also, oh, Joey's saying he's already trying, not looking forward to trying to get this across to my girls. It's very difficult actually, Joey, because, yeah, I'm not sure they're going to appreciate the little tricks in the same way, you know, like if you think of a number, oh, look, I know your number was this, and it's because you're using some sort of magic like this. I'm not sure how much that appeals to girls. I, myself, as a girl, love the precision of this. And, you know, that it all works out beautifully. And I think... go on.
I absolutely loved this when I was a kid, this sort of maths. But yesterday we were doing congruence, and a second set out of 6 in year 11 fell to pieces when I moved on to using the terms SAS, ASA, SSS. You know, so when you start then saying, right, we've got this concept of N, now I'm going to change it and group together some stuff and call it K, they're going to go berserk.
Yeah. I can definitely understand why girls, I hate congruence myself. I hate that aspect of geometry. I just, so boring. And I don't care.
Again, I love it because I love the way that, you know, if you've got a line with an angle at the other end, there is no other place that the 2 outside lines can meet, you know, unless you lengthen the line in the middle. You know, stuff like that, you know, visualizing all that sort of stuff, I just find...
Yeah, I remember
really...
I had to just learn those. I couldn't get my head around that as a kid, because it did not hold my interest at all, and I just had to learn them. And you know what? I don't think I even really did. That is a really... Did you get? And they were
the thing is, I put moving graphics up to explain why these things were so.
Yeah.
You know, in terms of proving congruence.
Yeah.
You know, and showing how you couldn't have anything else if you had two angles and an enclosed side.
Yeah.
And that was visual. This, I'm not sure how I'm going to take these concepts of proof, you know, for odds and even numbers, having designated them 2n and 2n plus 1.
Yeah.
You know, and take that further and make them understand it. I mean, to me, this is just really intuitive.
Yes.
And to most other people, and as I frequently say to a lot of my classes, you know, I appreciate I'm a complete freak, and that as an 11-year-old, I absolutely love this stuff.
Yeah.
And 99.9% of the rest of the population absolutely abhor it. But
yeah,
you know, we've got to try and drive through. But I just feel that with this sort of stuff, I'm up against a brick wall with geometry and you know, where we can start drawing shapes and colouring them in, and you know, that's fine. This stuff.
Okay, so so this is the sort of thing you could take forward as something to look into further, because I don't know any theory behind this particular aspect of teaching kids algebraic, the girls algebraic proof. But what I do know as a girl is that I really like to have, as a student, I really liked to have like I was saying about this literacy map this guy had, but basically a checklist. So if it says odd number, then it's going to be something to do with 2n plus 1. If it says even number, so like all the possibilities of what to think. So if you're looking for a multiple of 6, you need to take out a factor of 6. Basically, something that does the thinking for me, because the first problem they're going to have when they read these is knowing where to start. So it's just be unpicking each of these. So they've basically got a crib sheet, a glossary that says the sum, so add 3 things together. Consecutive means the ones next to it. Even numbers, 2n, and then the next even number is 2n plus 2, because it's 2 more than that. And just to go through all of that and have it, so they have it, or get them to make beautiful posters of it. It is one step. The initial teaching of it, because I don't know if that's where you come from, really. You see, I have always taught this in mixed classes, where I just give them, just like I have with you, just, on cards, because I've uploaded this. There are basically just lots of sheets with lots of these on, and you put them out, and they have to figure it out themselves. They have to put it into anything, or even if they're just writing about it. I don't know if it is, but maybe it is the boys, because I put them into teams. Maybe it is more the boys that come up with this initial idea. Well, there's also, I mean, again, we go back to Marcus de Soto and stuff. He's got a load of videos about proof. In fact, I'm going to show you one in a minute. And he does that. I'm just thinking about the sort of first step, generalizing. I mean, I think this is only for the GCSE and beyond classes. You're not looking at, they've got to have a strong grasp of algebra itself, haven't they, before they can get towards this, these sort of ideas. This is a typical AS question. So unfortunately, we don't know yet really what the new GCSE is going to be like in terms of proof, but this would be very, very high end of that. But yes, I am interested to know. So I will either look into it, or if you look into it, you could have a go about or ask Claire Baldwin about how, you know.
Well, as I said at the last night's study, this is pretty much my my assignment is generally girls in maths, but it'll be, you know, trying to get my head around why girls find it so difficult to do stuff like this, because there are some topics I've looked at over the last year where there has been nothing, you know, top set, bottom set, middle set, makes no odds, how engaged they are, how enthusiastic. There are some topics that you might as well just not do them, or talk to a brick wall.
Yeah.
You know.
And so, you know, you can basically take one of those topics, look into the theory of it, write something yourself, you know, with the teachers in your department or whatever, and try it and review it, and that would be your whole assignment.
Okay.
So yeah, it would be nice if we could fix it all, obviously, but one step at a time. So another acceptable way of proving something is to prove that it's wrong. Disproof. So before, when we looked, it was true both ways, that P imply Q, the converse is Q imply P, that was true, but it's often not. So n is an odd integer implies that 2n is an even integer. Yes, always the case. You know, 3 times 2, 5 times 2, any odd number multiplied by 2 is an even number. However, if you have an even number, the n is not necessarily an odd number, of course, because you just need one counter example. So you say, okay, well, the number 4, the n is 2, which is an even number, and therefore not true. So, prove that the following statement is false. For all integers n greater than or equal to 1, n squared plus 3n plus 1 is a prime number. We're just looking for the first counter example, or any counter example. Not even calculator, actually. Oh yeah, well done, Will. I'd been much more complicated and gone with 11. But 6 is 36 plus 18 plus 1, which is 55. Much easier than so I think in GCSE it's only going to be any of these sort of things that we've looked at. Some other methods of proof. At AS level, exhaustion is one of the ones they're given. I mean, that basically is where you can write down every single possibility and thus prove it. I can't think of anything that's really helpful. No, anything. But sometimes it's possible to write absolutely all the options down. Contradiction is where we assume that the theorem we've got is true and try to use the logic, the deduction, to work through it algebraically, and then we basically end up contradicting ourselves, and thus that means that it wasn't true, or Yeah, so we assume the opposite. I'll show you an example of it. And there's also proof by induction, which comes up only in further maths and then to do that, which is all based on if one of them is true and you can prove that the next thing is true, then everything else after that must be true. But I'll just show you a bit of contradiction. This comes up at A level, so it's not in the AS course, but it's in the second year. Often they're asked to prove something like, prove that root 2 is irrational. So you assume that root 2 is rational. That's your starting point. So if root 2 is rational, that means we can write it as a fraction. So let's say it's a fraction p over q. We'll say they're not both even, because if they were, we'd just be able to cancel by 2 anyway, and we'd have it down to the lowest. And thus, we may as well just stick with the lowest at the beginning. So if root 2 is a fraction, p over q, to get rid of this root, I square it. So I square both sides, so I've got p squared over q squared. So then I multiply up, so I've got 2q squared equals p squared. Now, I have got that if, so here I am again saying that it's even, but this suggests that p, in fact, is even because it's some number times 2, so it must be an even number. And if I square root an even number, I still get an even number. So I can say, okay, let's say that p is an even number, 2k. So that means that this is going to be, I've squared that separately. So I've got 2k all squared, which is 4k squared equals the 2q squared. So divided by 2, that means that q squared is 2k squared. So 2k squared, which means that q is even. So hang on, now I've got to a point where I've said that p is even and q is even, but I particularly said p and q are not both even, because otherwise I'd be able to cancel them down. Hence, I have a contradiction, and so that means that root 2 cannot be rational, because I cannot set it up in such a way that I don't then end up cancelling everything by 2. So the contradiction means root 2 must be irrational. It's a funny little proof, but one that they're expected to know at A level. Oh, here we go. Here is some proof by exhaustion. So have a go at doing this. Use the method of proof by exhaustion to prove the following result. No 1 or 2 digit perfect square ends in these, and state generalization. Here's for the time for a break, isn't it? So I have actually just written on there the proof by exhaustion. I've just been able to write down all the 1 and 2 digit perfect squares. 1, 4, 9, 16, 25, 36, 49, 54, 81. And by doing so, we can see they don't end in 2, 3, 7, or 8. What is the generalization of this result? Anyone want to have it again? So the generalization is that if, well, no 1 or 2 digits perfect squares end, we could have a look at the next couple and start to realize that, hang on, we could do all the 3-digit ones and 4-digit ones, and maybe see that actually no perfect square ends in a 2, 3, 7, or 8. So that would just be stating the generalization of this. And I have actually seen it in the exam where it says no perfect square, and it says prove that. And they're expected to sort of start with the 1 and 2 digit and say, okay, because those, none of those ends in 2, 3, 7, or 8, and everything else that you then make up after that is starting again. So once we get past here, do you see here? It then follows the same pattern again because the number that you're squaring. So 1, 2, 3, and so on. So then we get to 10. Then we've got 11, 12, and so on. Because this number at the end, when it's squared, gives you this number at the end. So the generalization is, as the numbers repeat, oh, sorry. I'm going to turn it off. Sorry. Hello? Right. Because they all end in the same numbers again, you will find that that then repeats. You're given the same numbers again. So that often proofs involve a little bit of writing at the end, and that's another thing that students hate, having to explain it. They, obviously prefer the ones, in fact, even with the ones where it just is sufficient to say 6 brackets n minus 1 or whatever, n plus 1, and they are like, okay, there you go, I've done it. This, you want them for good measure to say, and thus is a multiple of 6, so getting them to explain it back into words again is another difficult input. Right, I think I will, yeah, we'll just do this and then it's time for a break before we do cubics. So hopefully this will work. Is it making any sense? Yes. Can you hear this? Can you guys actually hear that?
No, I can't hear anything.
Okay. I'm just suddenly realising that I'm hearing it through my speaker. Let me turn this off. Sorry. I've been showing you this one before, have I?
I would like to excite
Oh, sorry. Right. Sorry, guys. I think it's time for a break now because clearly I'm. Let me try one more time. Right. Let me know when this gets going, whether you can hear it. Oh.
That they never write
down. Was anyone able to hear that? Can you hear me now? Very faint sound. Right. Okay. This is basically another of Marcus de Soto's proofs, and I think he's very good at explaining these things in a really interesting way that is good for kids. So I will leave it. It's in here, and I think this is. You can't hear me or the video. Can you hear me now? Have I plugged in the wrong jack? No. Oh, you can hear me, okay. Sorry. Good. Oh yeah, sorry. Yeah, not video. There you go. So in terms of teaching proof, using Marcus de Soto's proofs videos is generally my starting point. And I showed them to him, show them to them, and they're able to get an idea of sort of how these things work in their life. And then get into the sort of, doing the deduction and stuff by giving them lots of cards and getting them to try and figure it out themselves. And then giving them lots of, if it says this, then this, if it says this, then this kind of thing. And seeing how they're different. It's a very small part, I mean tiny at GCSE, and it's still pretty tiny at A level. But obviously anyone who then goes on to university, it is the whole of maths at university. There is nothing but proof. So, okay, it's a little bit, but it's not, but it's nearly all proof. So, although it doesn't seem important to them, it is. So, go and have a break, and then we will do cubics. Should we say 10 minutes? So that's 11:05. Okay. Are you back? Or is anyone back? Better question. Okay. So, Adam or Will, are you back? Let's do it. Well, I'll get started on talking and we can join us when he gets back. Oh, you're there. Good. Okay.
Sorry.
So the second half of this is about cubics. I say half, but obviously we really want to. Expanding and factorising cubics, sketching a graph of cubic functions, and using the factor and remainder theorem. Really, all of that is just about a mathematical exercise, really. So again, I don't think I've ever approached this from any sort of real life teaching. I think I very much started it from, right, you remember what you used to do with quadratics? Well, kind of perspective. So expanding and factorising cubics. I mean, I've never really had any issues with teaching this. It's quite a small little topic. Lots of the kids quite like it. But lots of them struggle with long division. I haven't actually put long division on there because, I'll talk about this later when you understand more about the cubics themselves. Right. So, in fact, here is the AS curriculum. Use the factor theorem and the remainder theorem. So you look at that. Carry out simple algebraic division. Restricted to cases no more complicated than division of a cubic by a linear. Yeah, do you know any more complicated than that? So actually, they are required to do that. So I was just about to say, you don't necessarily need to teach it to them. I do know people who, carry out simple algebraic division. It doesn't say how. So just like numeric division and the fact that we have like the bus stop method or other ways of doing it, it's the same with algebraic. I like algebraic long division because I love algebra and manipulating things so that it all falls out. Whereas a lot of the kids get themselves in a right muddle with it. As you can imagine, if you've ever seen a kid do regular long division. this is actually saying the same thing as that, really. I think that must have come from a different board. Use the relations between the symmetric functions of the roots of polynomial equations and the coefficients. Use the relations between the symmetric functions of the roots. What are the different cases? Use a given simple substitution to obtain an equation whose roots are related in a simple way to those of the original equation. I think it's just saying factorize them. Simple things to obtain an equation whose roots are related. I'm going to ignore that because I actually have no idea what that means. I can't be bothered to think it through. So, I think the first word to introduce them when they get to AS and to doing this is polynomials, because they've talked about linear and quadratic, and the family of them are the polynomials, so they should know that. So a quadratic polynomial, a cubic, quartic, just depends on the highest power. So cubic functions expansion is fairly straightforward, provided the kids are all right with their quadratic expansion. If they are not all right with their quadratic expansion, they shouldn't really have progressed onto AS or A level. That's probably, in fact, something that you should get them to do when they come in and they say, I'd like to do maths at AS or A level. You say, okay, expand a quadratic for me. And if they struggle with that, then they are going to struggle for the rest of the year. Because really, that is the bread and butter of everything. So, to expand a cubic, expand two brackets. It doesn't matter which ones you choose, but just choose two of them and expand those together to create a new bracket. So x squared plus 2x minus 5x minus 10 multiplied by x plus 1. Generally, we collect that together. So we've got x squared minus 3x minus 10 and x plus 1. Now, you just have to take care because, like we did here with the 2, and we multiply every bit by every other bit, we have to do the same. People do it in various different ways. No, there's two different ways. They either do x squared times x squared plus 1, minus 3x times, so they do each one like that. Or the other way around, you do everything times x and then everything times 1. So this one says multiply each of the 3 terms in the first pair of brackets by each of the 2 terms in the second. It doesn't say particularly what order to do it, but they've gone that 1 times x and then all of that times 1. And I think that's probably easier, or less likely to lose anything, if you just do that 1 times that, that 1 times that, that 1 times that. You do see all sorts of messes where they've gone, oh, I've got that one, and then I've got that one, and then I've got this one, and you're just like, just do it in an order. Be organised. This is particularly organised, doing it like this, writing one below the other. And it's quite nice because you can then just draw a line under it, add it all up, and it collects the terms for you. But obviously writing it in a line is no big hardship, is it, to collect together x squared and x term. So have a go at doing this one yourself. Right, have we done that? Do it. Oh, I thought +6. -3 times -2. In fact, I know that's the case because...
Yes,
yeah. And in fact, so Will has put x cubed minus 7x plus 3, and the answer is x cubed minus 7x plus 6. So,
yeah, I made a mistake in my arithmetic with the integers.
Very easily done. But this is why actually one of the really nice checks to get the kids to do, and helps them when they're doing graphs anyway, generally using cubics, is to understand that the number they're going to have at the end is going to be all of these three numbers multiplied together. So they'll know that they're going to get 3 times a -1 times a -2, so that's going to be +6 at the end. So yes, so that's a good check. Any issues with doing that? Any questions about it? So let's get on to these theorems that it's talking about. Nothing too complex, really. The factor theorem. Here we have a graph. It's the function x cubed minus 6x squared minus x plus 30. What do you know about its solution? What do I mean? What is the solution? It's very poorly worded actually, because really, I should say, what do you know about the solution to the equation when the function is set equal to 0? So when this equals 0, what do we know about that solution? Jerry, yes.
It's got 3 real solutions.
Yes, absolutely. 3 real solutions.
Because it crosses the x-axis 3 times.
Exactly. Yeah, and there's the full square crosses the x-axis. So we know that 3 distinct solutions and y equals 0, and basically we want to find those values of x. Now, to find these values of x, what we know is that they must be factors of 30. So this is what I was just saying before. When we've got it factorized, and you multiply the 3 numbers together, you get this number at the end. And going back to the factorized form, what this actually means, doesn't it? If I was to make each of this, if I made this equal to 0, then that would mean that either x plus 3 equals 0, so x equals -3, or x minus 1, and so on, just like when you're solving a quadratic. So here, we know that they must be 3 solutions which multiply together to get 30, so they're factors of 30. So we know that we can factorize this, well hopefully we can factorize it into 3, otherwise we've got a few issues, because we've got 3 distinct solutions, so it should factorize into 3 distinct brackets, with the solutions being A, B and C. Question is, how do we find A, B and C? If you were to leave this to a student, if I leave it to you, what do you think that you might do to try and find A, B and C? trial and error. If you were to leave this to the students, they would probably just try numbers. And amazingly, on this occasion, they would be absolutely correct to do that. Because actually that is what we do for the fact theorem. To find A, B, and C, which this in fact is this when we've done it. Cool. Oh, in fact, I've taken it back. So, when we look at a quadratic, we know that we're always looking for two things that multiply to get that, because that's the same issue, that the two numbers at the ends multiply to get that. So we know that it's going to be -1 times 3. So the solutions are that x is 1 and x is -3. If we then put that into the function, so f of 1 means replace the x with the 1. 1 squared plus 2 minus 3 equals 0, which confirms that that is in fact a solution. Same with -3. So when we put the solutions in, we get 0. That is basically the factor theorem, and enables us to factorize cubics, because if we want to find out what the how to factorize this cubic, we need to find those factors. If we look at the end number, the 3, we know that it's got to be 1 minus 1, 3 minus 3. We've got 4 possibilities. So we start with the first possibility. Okay, I would have started with 1, they've started with -1. Fine. So f of -1, put it into here, -1 cubed plus 7 minus 9 plus 3 equals -1. Doesn't equal 0, so -1 is not one of the solutions. Oh, sorry, wait. No, it does equal 0. Right, must click through. Okay, so I was wrong. -1 is one of them. Okay, so -1 is one of the factors of 3 and gives a solution. Now that means, so -1 is the solution, which means x plus 1 is the factor of the whole thing. That is the bracket that it becomes. Is that clear? This is one of the issues that students have. The difference between the root and the factor. So x equals -1 is one of the roots. It is one of the solutions for the x value of where it crosses the axis. That is what we put in here. When that's then a factor in brackets, it becomes x plus 1, because obviously x plus 1 equals 0 means that x equals -1. So this is the factor theorem. If f of a is 0, then x minus a is a factor, and vice versa. So if x plus 1 is a factor, then f of -1 will give you 0. This is helpful because we can then keep going with this one that we found. So this is a different one, in fact. Here we have our function, x cubed minus 2x squared plus 3x minus 2. We know that the possibilities that we need to try for the possible roots are going to be -1, 1, -2, 2. They've started with 1. So f of 1, they put into here, they get 1 cubed minus 2 plus 3 minus 2 equals 0. Yay. So if f of 1 equals 0, then x minus 1 is a factor. That is what the factor theorem states. So we have found one factor. We can keep going and find lots of them like this. In an exam, if the students are completely stumped and can't do the next bit, they are awarded marks if they just try each of the different ones, because they're going to find they've only got 4 to try here. 1, -1, 2 and -2, and they'll be able to find the factors. However, it may be that there are not 3 distinct routes, in which case they end up a bit screwed. Anyway, the process they're supposed to go through is that they find one factor. Once they've found one factor, they can then use that to find the remaining quadratic. So here we are again. We find the first factor. They're factors of 8, so we've got many more options. 1, -1, 2, -2, 4, -4, and 8, -8. I generally get them to start with 1, and progress upwards. This is generally on a non-calculated paper, and there's no point with them stressing themselves out with 8 cubes. F1 doesn't give us any hope, so x -1 is not a factor. So they're going to try f of -1, and that helps. And yes, you get a feel for it. Now, part of the issue is you've got to make sure they're really clear with their signs, because they so easily could have just miswritten it, ended up with 0 and thought that was a factor. And I see that a lot when marking with exam papers, that they think that they found a factor and they start down that path, and then they can't figure out why they can't actually factorise it properly, and don't think to go back and check its original working. So x +1 is a factor. Great. So we know that will be one of these brackets. We know that if we have the x +1, it will be multiplied by a quadratic in order to get our cubic. Now we just need to find that quadratic. There are 2 ways to do this. Inspection, which is basically equating coefficients and looking at what's happening, or there's division. This PowerPoint, because this comes from the Teach A-Level Maths PowerPoints, he prefers to do inspection. A lot of people do, and the kids, it's useful, it is useful. I prefer long division. They can do either, and you can teach either. You can teach both. So, inspection means just considering what is missing. So we need to get the x cubed and the +8. That's sort of the easiest thing we can do. We know that in order to get an x cubed, we're just going to need to multiply by x squared. And to get the 8 from the 1, we're just going to need an 8. It's the bit in the middle that's a bit more complex. And this is where it involves sort of a bit of muddling things around to get there. So I don't like this as much because I find it, well, basically it's less precise. You have to actually use your brain a bit more. The long division I just do kind of on autopilot and the answer falls out. Whereas here I find myself going, okay, I need -2x squared. I've got 1x, so I need to take off 3x. Okay, so I want to take off 3x squared. Right, let's do that. Okay. Now, does that then work with the final bit? I wanted 5x. I've already got an 8x. I take -3x. Yay, it works. I know it's not exactly taxing, is it? But I'm just a big division. I don't think the kids are though, so this is probably more of the way to go. So we've now split our cubic into our initial factor and a quadratic. So then we just need to check, can I factorise this? And they might spend a lot of time to try to figure that out. But in this case you can't. That is it, fully factorised. Now, long division, if we just start with very basic linear factors and write it as the bus stop method, you can go down the road of doing it all with numbers first. I've done that once, and I found it just confused the kids because they're never really a big fan of long division with numbers in the first place. So I tend to just teach this. How many times does x go into 2x? 2 times. So we're just going in, using the first term of this, goes into the first term of that. I say numerator and denominator because we could just write this as a fraction of 2x plus 6 over x minus 1. So 2x over x is 2. We just write that generally above the number. And then, as they do, you say, okay, so how many x minus 1s have I got? 2. 2 of those means I've got 2x minus 2. So I then write that in basically below here. I then draw a line under it, take them away from each other. 6 minus 2 gives me 8. And that's my remainder, in fact, because this isn't going to go in anymore. This is simply this. So I've got 2 lots of x minus 1 plus an 8 over x minus 1, because that's how many bits I've got left. So we can do this with a linear into a polynomial. It just extends how many things you've got going on. Oh yes, sorry, because of this bit about remainders, I thought I'd start on about remainders next, actually. I will come back to long division. So, we're just looking at the moment, we've looked at the factor theorem and how when we try numbers, possible roots, then we know whether it's a factor. And we use that to find a linear function, a linear factor, to divide in, find the quadratic. If we actually applied the factor theorem using any number, what it actually does is find the remainder. So to find the remainder when this is divided by this, we can divide in, but it's much easier to use the factor theorem and say, okay, if it's divided by x minus 1, that's actually the same as substituting in when x equals 1. So f of 1 is 1 plus 7 minus 4, which gives me 4. So that means I know when I divide this by x minus 1, I have a remainder of 4. And that's what the remainder theorem is basically. It just says, if we divide a polynomial by x minus a, the remainder is given by f of a. It's still exactly the same as the factor theorem, in fact, it's just that when that happens, and it is a factor, it will just be that the remainder is 0. This little bit of proof of the remainder theorem is not required. It's purely for your academic memorization. So the proof is saying, okay, if I've got a polynomial f of x, I divide it by my factor, x minus a, and I end up with another polynomial plus the remainder over the original. That's what we know. If we think back to numbers, if you divide 3 and then if I divide 3 by a half, I've got, no, that's ridiculous. If I divide 3 by 2, I end up with 1 plus 1, remainder 1, over 2. And then because I've got 2 times 1 gives me the 2, I've got a remainder of 1, which we put over the original divisor, giving me 1 and a half. That's the same as here. If I now just multiply everything by x minus a, I end up just with this bit multiplied, so f of x is factor times this new polynomial plus r. And this, you can see, is the case with the linear factor times the quadratic. And normally that would be plus 0 if it's a factor, or plus a remainder. Now, if we substitute in when x is a, we end up that this bit here is 0, and therefore f of a equals. So that's the proof of the main thing. Anyway, what I want you to do, well, actually I might do this quickly now. This is most commonly used, the remainder theorem is most commonly used just to set up simultaneous equations. They tell you some things that you know. So they told you x plus 2 is a factor of this, and that if you divide by this, you get this remainder. So we know that f of minus 2 is 0. So if we sub minus 2 into here, we end up with an equation involving a and b. We also know that x minus 1 gives this remainder. So instead of f of minus 2 equaling 0, we now know that f of 1 equals minus 3. We end up with another equation, and now we've just got 2 simultaneous equations that we can solve, find a, find b, and thus, given that information, we know that our original cubic must have been x cubed plus 3a squared minus x minus 6. So that's a very typical exam question that they like to give. Here's one for you to do yourselves. So have a go at doing this yourself. Are there any questions about what I've been watching about? Yeah, okay, well, have a quick go at doing this. Right, what do you get? Yes. Good, Evan. 13. So, this is a very simple question. Would be worth 1 mark, maybe 2, in the exam. But because it's got the words divided by in it, the students head down all sorts of routes, often doing long division, which is absolutely fine. They get the answer, but it's just taken them a really long time, when all they needed to do was use the remainder theorem to put in F2 and get 13. Yeah, absolutely, and use the remainder theorem to check. It's quite a useful way to check each other thing. Okay. So, to factorise a cubic, We use the factor theorem to find a linear factor. We then divide it in to find the quadratic and then see whether that happens further. So as I've said, I prefer to use long division to find the quadratic. So what I thought I'd do is show you this because I think, yeah. So this is going to involve me using the pen and probably writing very slowly. So I'm just going to work through one complete thing as I would do. And then you can decide on the next couple of exercises whether you want to use inspection or long division. It's totally up to you. So to factorise this cubic, I know that I need to look for factors using the factor theorem. The factors are possibly 1 minus 1, 2 minus 2, 3 minus 3, 6 minus 6, because that's what goes into minus 6. So f of 1, I'm going to get 1 plus 2 minus 5 minus 6. So that is not going to help me. And I don't think minus 1 would help me either. F of 2 is going to give me 8 plus 8 minus 10 minus 6, hooray, that is 0. So because one of the roots is 2, I therefore know that x minus 2 is a factor. And it's important to get the students to write that, because doing that will get them a mark, doing this might get them another mark. So if that is a factor, then I can divide this in to my cubic. So I set up my bus stop. Oops. X cubed. X squared. X into x cubed goes x squared times. The students find that in itself quite tricky, which is why in that previous slide they wrote it as the fraction that it is, because it's basically it's x cubed over x. They might find that easier to see because in terms of cancelling they can say, oh, okay, so that is with x squared. So x into x cubed goes x squared times. Encourage them to write that over the x squared term. We then go down the case of saying, okay, so I'm going to have x squared amount of these. So x squared times x is x cubed. Write it underneath. X squared times minus 2 is minus 2x squared. Draw a line under that. Subtraction sign, and I'm going to be going x cubed minus x cubed is nothing. 2x squared minus 2x squared. So 2 plus 2 is 4x squared. I'm showing you this now and I really like it myself, but I see why it's just a complete walking disaster, because there's just so many places the students can go wrong, and they often do it with signs. Here we are again, x into 4x squared now. So this is the next stage. They're down to here now. This is their new thing. Okay, really what they're now doing, if you wanted to, they could then do this again. I don't generally do this. It's the first time I've ever done this. But it might be wise because so many students seem to forget exactly what they're doing now. We're just here now. We're now doing x minus 2 into what we've got left after we've taken it off x squared amount of our bit. X into 4x squared goes 4x times, which I write above this. And here I go again. 4x times x is 4x squared. Now, I know here what I've done is like set up a new division thing, but normally what I do is I just say, okay, I've got to bring this down so that I've got my minus 5x from above, and then x, oh yeah, sorry, x times 4x is 4x squared, minus 2 times 4x is minus. Draw the line again, take it away, nothing. Minus 5 minus minus 8 is 5 plus 8. I'm not doing this correctly, that's good. Okay, well, we'll see how it goes. Minus 5 plus 8. Right, well that would be it, wouldn't it? There you go, sign, so easy. Minus 5 plus 8. Luckily, the fact that this looks like this looks like I did it correctly in the first place, because it should in fact be 3. Okay, so that's just a 3x. I bring down the minus 6. And now my new division is x minus 2 into 3x minus 6. So x into 3x is 3 times. So then x times 3 is 3x. Minus 2 times 3 is minus 6. Thank goodness. And I know from doing that, obviously, that works because I'm left with 0 at the bottom. Obviously, when the students get to here and it doesn't work, they know they've made a mistake somewhere. It's then just a case of spotting it. If I'd progressed my 13, well, it would have been silly, because obviously I knew right away that that wasn't right, because I could see nothing was going to kick me into 13. But it is quite difficult to track back, and I often get, in the exam papers, I see like 4 different sets of long division done. So I now know x minus 2 is my linear factor, x squared plus 4x plus 3 is my quadratic factor, and all that's left to do is to factorise that bit again. So there'll be something involving plus 1 and plus 3, isn't it? So this one actually says factorise this completely. Often it will say solve this equals 0, and a lot of students stop here and forget that they then need to say x equals 2, x equals minus 1 and minus 3. So that is the approach I take. Instead of all of this massive bit here, then obviously we could have done inspection just as we did before, where we're saying we need to multiply it by some quadratic to get this. And we would have known, okay, to get x cubed I need an x squared, to get minus 6 I need a plus 3. And then to get the bit in the middle, I need, I've got minus 2x squared, I need plus 2, so I'm going to have to add on 4 x's. Yes, that is a lot quicker, isn't it? I'm finding that I need to eat my words here, but I think it's tricky. I think one of the key things is check very clearly on your syllabus whether it states they particularly need, because it depends on the exam board, they particularly need to do long division, or whether inspection is always sufficient. Whether they are basically saying, can you do this process, or do you just need the solution? And ultimately, well, really, you just need to be able to get to this, don't you? This is very powerful, obviously, because it's all very well with inspection here. It's fairly simplistic. But this enables you to be able to divide anything into anything. What do you guys think? What do you think you're more likely to try?
second method seems a lot more straightforward once you've established it's a factor and using the remainder theorem. It's obviously going to have to multiply something to make that cubic expression or a cubic function. Therefore, just finding that's very straightforward, rather than essentially sort of for long division method, where a slight error can lead you down the rabbit hole of what I think the students will see as a lot of wasted effort because they've made a basic mistake early on. They're going to have to retrace their steps because it's systematic. You actually teach them the second method.
Yeah.
Or teach them both methods and say this one is probably going to be far more useful to you, particularly in terms of exam situation, because it's far harder to get that done along method. With that, therefore you can complete the question relatively quickly with a decent assurance that you're right, provided it's.
And I think there was a general push anyway to teach long division, because I think it used to be stated that they needed to know it specifically, and also, you know, for broadening their maths abilities. And so I always started by teaching long division, and then was like, and here's how we use it. And then one year, one of the students sort of went, well, God, I just do inspection, and just did it. And I was like, oh, yeah, okay, that's nice. You could do that then, but I'm going to do this way. But now when I've sort of talked it through with you guys, I think it's tricky, isn't it? If you felt that you were tight for time, no, you see, I still feel, you know, these are A-level students. They should be, you know, doing the long division. Anyway, you guys can decide if you are now going to have a go at doing these yourself. And have a go at doing these in whichever way you prefer. Or try both ways. Actually, sorry, I just want to say one more thing about long division. Something that really catches the students out with long division is the occasions when say it doesn't have this bit here. It's only got x cubed minus 5x minus 6 because it happens to not have an x squared term. Make sure they put in a 0x squared, because leaving a gap, they often squidge it up and then completely muck it up later. Is it just me, or is anyone I was struggling to find the factor for the first one. Oh, no, it's because I had a completely bit of journal. I'm just going to click through because no. Has anyone found a factor for this? I think I've mistyped it. I don't know. Yeah, I think we're going to have to say -4 because unless it was a trick question, I cannot find the factor of that. So let's say that that is -4 and hope that works. sorry, I've just seen that it's gone past 12, so that went incredibly fast. Just to give you the answers, and you can then check. So we can definitely say that it should be a 4. When you then put that in, you get that 1 is a factor, or equally you might have found that 1 is a root and 4 is a root. So when you end up factorising it, you get x minus 1 is a factor, 2x minus 1, and x minus 4. By inspection, I found I got a bit of a muddle actually with the signs, and it was actually easier when I then did it by long division to check. For this one, to show it's a factor, we just need to say, okay, if it's a factor, then 3x minus 1 equals 0. So that means that x equals a third. And you sub that in and you find that that does give you 0. A lot of the students, when they're asked to show something as a factor, don't realise that they really have to properly show, so that's a third cubed. Then work out the next step. They've got to show all that working in a show that. You can't just go, I'll put a third and it's 0. Because we knew that. Factorising this completely is one of those situations that because it's actually missing an x term, you do end up with 3x minus 1 and x squared plus 4. So just beware, because as you do that, if you do that as a long division, you end up with 0 for the first bit, but that's just the same as when you divide something exactly. You then just go on to the next bit. So you then just say, okay, 3x into 12x is 4, and continue from there. So that was cubics. There's, as you see, not very much to it. Next Wednesday, I'm going to be doing differentiation and integration with you. Calculus, basically. Really helps if you're good with your indices. So brush up on those if needs be for next Wednesday. And I will see you next week. I might see you around on the Tuesday as you're registering, but I will definitely see you for supper. I will definitely see you on the Wednesday when I will be able to tell you more about calculus and answer any questions that you've got. And yeah, have you got any questions for me today? No, you're right. You know what you're doing for Huddersfield. You know where you're going and that's the thing.
Yeah.
Great. Okay. Okay, I'll stop recording now.